Suspensions can settle, and they can be filtered. So you can set a filter paper in a funnel, pass it through, the solid will stay in the filter, and the liquid will come through. So you can separate it relatively easily that way. Colloid won't do that. A colloid, the particles are so small that it'll still pass right through a filter. It can only be separated by what we call a semi-permeable membrane. We're going to use these on Monday in lab. So let me show you a picture of this because I don't want to draw it. So you've got you've got your stuff here, all this different stuff that's in this water. The yellow stuff is in solution. The blue stuff, those little triangles, are colloid, and the red squares are the suspension. So if you shake it all up, it all kind of disperses through it. If you let it settle, the suspension particles settle down to the bottom, but all the other ones are still held in with the water. You pass it through a filter. The red suspension particles are filtered out, and maybe a couple of the colloid ones, but most of the colloid makes it through and all the solution makes it through. And then you use what's called a semi-permeable membrane. So you put it in this special kind of a bag. It's kind of like a plastic wrap, is like a semi-permeable membrane. And the solution particles in orange here can actually get out of that bag because they're small enough that they can pass through it, but everything else is trapped inside. So this is what we're going to look at on Monday. We'll look at some starch particles, which will not go through the semi-permeable membrane, but then some ions will go through that because they're in solution. So as we're talking about semi-permeable membranes, we need to talk about osmotic pressure. This is a really important concept in medicine. Does anybody know what osmosis is, what that means? Yeah, there you go.
It balances like the solid things you have on one side and like tubing. This thing I've seen in my last class is like you have water and solid stuff and it has to balance itself out to the pressure percent.
Yeah, so osmosis is the movement of water, diffusion of water through a semi-permeable membrane. Meaning that it's a membrane, meaning it's kind of, a membrane is like a material, like a filter, but the holes in it are so small that only individual molecules, small molecules, can get through it. So water can get through it, solution particles can get through it, but anything bigger really can't. So osmosis is that water moving back and forth through that membrane. What you can do, and again, I'm going to grab a picture from the book, because I don't think that it will look so good if I try to draw it. If you set up a semi-permeable membrane like this, and we'll do this on Monday, water can easily pass back and forth here. So in this example, you have a sucrose solution, a sugar solution. And there's a bunch of sugar dissolved in this side, but there's no sugar dissolved in this side. You have a semi-permeable membrane that can pass water back and forth. What happens is, over time, the side with the sucrose solution in it will start to fill up with water. So what the water is trying to do here is trying to equalize the flow. And in order to equalize the flow, the concentrations need to be the same. So if you ever have two two solutions separated by a semi-permeable membrane, and the concentrations of ions are not the same, or of particles are not the same, water will flow from the area of low concentration to the area of high concentration until those things are equaled out. And that flow, or that push against that membrane, is known as osmotic pressure. So this is this pressure that this water is exerting, pushing this thing up. Now this is important in a lot of areas, but particularly in your body. What are the semi-permeable membranes that we're dealing with in your body? Cells, yeah, cell membrane. So there is osmosis going on as water is passing in and out of cells. And if the concentrations aren't relatively equal, then you can have too much water going into the cells, which causes them to burst, or too much water going out of the cells, which causes them to collapse. Right. So we're going to talk about 3 different situations of solutions that can go in your body depending on their osmotic pressures. And those are called isotonic, hypotonic, and hypertonic. Iso means the same. So an isotonic solution is going to have the same osmotic pressure as, we'll just say bodily fluids. But blood or anything that comes in contact with cells. So this means that if you put an isotonic solution in your veins, it's not going to mess with the cells at all. It's going to have the same osmotic pressure, so there's going to be even flow of the water in and out of the cells. And so most like intravenous solutions that you would use would be isotonic solutions because you don't want it messing. But sometimes you do. All right, so a hypotonic solution has a lower solute concentration. It's less concentrated. Hypo means less. So a hypotonic solution is less concentrated than your bodily fluids are normally. So let's think about what happens in that case. So here you have a cell that has higher concentration of stuff than the fluid around it. So if the cell has a higher concentration than the fluid around it, which way does the water flow? Does it go, what? It's going to go into the cell to try to equalize the concentrations. So the water is flowing from the outside into the cell, which does what to the cells? Swells them up, right? So you can do the same thing like with a raisin. Everybody know what a raisin is? It's like a little dried grape thing. So you throw a raisin in water, that water is going to have a much lower concentration than the fluid in the raisin. And so after a while, the raisin kind of swells up.
Really?
Yeah, try it.
Oh.
Just like a bad grape at that point.
Yeah.
Great.
Yeah, it just is like a bad little grape. Yeah. So then the opposite is going to happen in a hypertonic solution. Which is going to have a higher solute concentration. So we've got our cell again. And now our solution around it is much more concentrated, which means the water is going to flow out. And that's going to cause the cell to collapse. Anybody ever made pickles? Yeah, pickles are good, right?
Delicious.
But pickles are also tend to be a little bit smaller than the cucumbers they came from. They tend to shrivel up a little bit. And that's because that pickling solution is hypertonic. That pickling solution is full of salt and vinegar and other dissolved stuff, flavor molecules. And so it's going to pull some of that water out of the cucumber and make the pickle. So on a cellular level, we can look at some pictures of this with respect to blood cells. So here are some pictures of these things. So normal isotonic solution, I'm going to turn the lights off a little bit so you can see that better. You're going to see that the blood cells look like regular old blood cells. Nothing really happens to them, and that's what they're supposed to look like over here on the left. You have a hypotonic solution, lower concentration solution, which means that water is going to flow into the cell. So that's the raisin situation. And ultimately, that causes the cells to burst. So you have a hemolysis. Hemolysis is the bursting of that cell due to too much fluid going inside it. So you see they're losing their middle kind of donut-looking inner tube shape, and they're starting to swell and then ultimately burst. And then the opposite of that, the pickle situation, you have the water flowing out of the cell, causing it to kind of collapse on itself. And that's called crenation. When the water leaves the red blood cells, it shrinks and then ultimately is destroyed. Okay. So sometimes you may, normally we always want isotonic stuff in our body because we don't want those things to happen to ourselves. But sometimes in medical emergencies, you're going to want, under careful supervision of a doctor, you're going to want to be in one of these other situations. You can think about what happens to your blood volume. So if you have the middle situation where you put a hypotonic solution in your blood, now fluid is going into your blood cells, which means that your blood volume is getting smaller. So that means that you have basically less blood moving around in your body, which can be good in some situations to concentrate the blood more. More commonly in the other situation, if you really need to increase the amount of fluid in your blood, if you're having collapsed blood vessels and you really need to open those things up, like an emergency, you might introduce a hypertonic solution, which will draw some of the fluid out of the blood cells quickly and make your blood volumes become greater very quickly and can help with some of those things, like if you're extremely dehydrated or something like that. So that's what those situations mean. Now, the thing that's very confusing about these, go back up to our discussions here, is to actually think about it in terms of osmotic pressure. So a hypotonic solution, is that exerting a greater or a smaller osmotic pressure on the cell? Greater, because that pressure is pushing into the cell. So the direction of the osmotic pressure in a hypotonic solution is positive. It's going into the cell. It's a higher pressure. And that confuses people because the word hypo means lower. So we have to keep straight that this hypotonic refers to the lower solute concentration, not to the difference in osmotic pressure. You actually have a greater osmotic pressure here and a lower osmotic pressure, or a negative osmotic pressure here, because the water is pushing out of the cell in that direction. All right. This is also related, besides just in your blood, This is also important to what we call dialysis. Anybody know what dialysis is? It's a filtering of blood. What's filtering?
They're filtering out the waste.
What kind of wastes?
Because the person's kidneys aren't working
Mm-hmm.
effectively, so maybe toxins and stuff out of the body. I'm not explaining it right.
No, you're right.
Someone's on dialysis, they're literally pee.
Yeah.
All the waste is gone.
Right. So you've got, and we're going to actually see this on Monday. It'll make a little bit more sense. So your kidneys are dialysis membranes. So dialysis is related to osmosis, but it's kind of, instead of talking about the water moving in dialysis, we're talking about the solutes moving. So when blood goes through your kidneys, the solutes, the waste stuff that's dissolved in your blood, goes through these membranes in your kidneys to then go out and be disposed of in the urine. If someone's kidneys aren't working or they don't have kidneys or something, then this has to be done outside the body. So you go to a dialysis place, they take your blood out of your body, pass it through a synthetic dialysis membrane, and then put it back in you after all that stuff has come out.
All of your blood?
No. Well, it depends how many times you have to go and how long they. Yeah, it's a long process. What? Yeah. But I mean, it works. You know, people can live for many, many years just having regular dialysis. It's not pleasant, but it's, does the job. And so, so that's dialysis. So the difference between dialysis and osmosis is the motion of water. Dialysis is the motion of the particles. But we're still talking about things going back and forth through a semi-permeable membrane like that. Okay, and then so the last bit, the last thing that you might see here, we'll go all the way back up to this example, is looking at what we call reverse osmosis. So what does anybody know what reverse osmosis is? What? Yeah, it's the same process. What's it used for? Where have you heard? Has anybody ever heard that term reverse osmosis in the context of anything? It is the opposite. It's used for purification. So if you have some bottled water, chances are that it says something about this is reverse osmosis water or purified through reverse osmosis, something like that. And what that is it's doing the opposite. So instead of taking a situation like this and letting the water flow using the natural osmotic pressure that'll flow into here, you do the opposite. You take some kind of machine and you pump the water through this way. The particles have to stay behind. The water pushes through this way. And so that purifies this water because everything else has to stay behind that semi-permeable membrane. So it's a very effective way. It's expensive and can be slow, but it's a very effective way to purify water. And you can actually get reverse osmosis systems in your house. If you have well water or something like that, you need to purify it. You can use osmosis, the opposite of osmosis, to purify the water by flowing it through that semi-permeable membrane. All right, so that's osmotic pressure. Questions about that? So a lot of times what we'll talk about is what makes an isotonic solution or what makes a hypertonic solution. And we can calculate this based on the concentrations. So a 0.9%, is it saying? Yeah. 0.9% mass to volume NaCl is isotonic. and a 0.3 molar solution of glucose is isotonic. Where this gets tricky is we have to remember that the osmotic pressure is controlled by the number of particles that are dissolved. So let's convert these to the same unit and show how they're the same. So I'll do it one way first, and then you can work on the other way. We'll do the harder one together, which is going from NaCl to glucose. We actually did this last week, but we'll go through it again, and we'll in this context and show how it's different. So 0.9% moles per volume NaCl, let's convert that to molarity. First, what we have to do is realize that 0.9% mass per volume means grams divided by milliliters, right? You remember that? So we don't know exactly how much of the solution, so we can just pick a nice round number, which means if it's a 0.9% solution and you have 100 milliliters, how many grams of sodium chloride do you have? In 100 milliliters, and you want 0.9%. You just have 0.9. So we're going to pick that as our volume just to make it nice. So a 0.9% solution is like saying 0.9 grams of sodium chloride per 100 milliliters of solution. So now we're going to do what we did last time and convert the grams to moles and milliliters to liters, because we know that molarity is moles per liter, moles of solute per liter of solution. All right, so that's going to be 0.9 grams sodium chloride. And then we're going to get rid of grams and have moles instead. So sodium is 23, chloride is 35.5. So it's going to be 58.5 grams per mole. And I think we did that earlier, so I'll just go back and look at our numbers. That is 0.0153 moles. Where? 58.5. And then 100 milliliters. We know there are 1,000 milliliters in 1 liter. So that's 0.100 liters solution. Okay, so now we have moles of solute, NaCl, and we have liters of solution. So we can put those on top of each other and find our molarity. Remember, molarity is moles per liter. So 0.0153 moles of solute divided by 0.100 liters of solution means that our concentration is 0.153 molar NaCl. So let's compare that now. How can 0.3 molar glucose be isotonic and 0.153 molar NaCl also be isotonic? Any idea how those can actually be the same concentration? Are they really close?
Have the same amount of dissolved particles.
Right, we have to think of dissolved particles in total, not just overall formula units. So look at how we wrote this. We have this many moles of NaCl. But remember, NaCl is really two ions, a sodium ion and a chloride ion. So if we want the concentration of total ions, we have to realize that there are, in each liter, we're going to have 0.153 moles of sodium and 0.153 moles of chloride. So if our solution is 0.153 molar in sodium chloride, that means we're going to have 0.153 moles of each type of ion. So our total ions then are 0.306 molar. So the total concentration of all ions in the solution is 0.306 molar. We usually don't talk about total ionic concentration in terms of the chemistry of it, but in something like osmotic pressure, that's what's important. So now we can see how these are actually the same or similar, 0.3, 0.3. Glucose is not ionic, that's a single molecule. So if you have 0.3 moles of glucose, that's 0.3 moles of particles. And if you have 0.3 moles of total ions, that's 0.3 moles of particles. So let's go backwards then. And do it the other way. Let's express 0.3 molar glucose in percent mass per volume. And you're going to need to know that glucose, the formula of glucose is C6H12O6. So see if you can kind of do what we did, but backwards. Start with a molarity, a moles per liter, and go back to percent mass by volume.
It's still in 100 ml.
Well, molarity is actually moles per liter. But that's right. We have to turn moles per liter into grams per 100 milliliters. Or grams per milliliter. It'll be easier to do it this way. Just moles per liter to grams per milliliter times 100%. All right, so you can convert moles to grams, liters to milliliters, and then divide. Let me see what's going calculus. So you're going to take that 0.3 moles per 1 liter and convert the 0.3 moles to a certain number of grams using the molecular weight. I guess it's a pretty good job in this. We can't do it all together at once. So just convert the grams, or the moles to grams. And then you're just going to divide that by 1,000 milliliters.
So that number, after you divide the total molecular weight divided by 1,000 times, yes, this is the molarity.
No, that's the percent, so it's going to be 1.8%. Yeah, so let's look at this again. So 0.3 molar means 0.3 moles per 1 liter. Now we know 1 liter is 1,000 milliliters, right? So we can leave it like that. But now, since we want grams per milliliter, we have to turn this moles into grams. So 0.3 moles of C6H12O6 how many grams is that? Did anybody calculate this out? What and what? 192?
192 grams.
So 192 grams per mole. So what does that come out to? 0.3 times 192. So that's 57.6 grams of glucose in each 100 milliliters. All right, so we're saying 0.3 moles is 57.6 grams. So what we can then do is put this on top of the 100 milliliters, so 57.6 grams, or 1,000 divided by 1,000 milliliters times 100%. And that's going to be 5.76%. So we can say that a 5.76% glucose solution is also isotonic. So anything with a concentration above that is going to be hypertonic, and anything with a concentration below that is going to be hypotonic. Now, when you look at an IV bag, it'll often be in different units. So something like sodium chloride will usually be given in a percentage, like 0.9%. Something like glucose is often given in a molarity, so 0.3 molar. And of course, there's all kinds of other stuff that could potentially be in there that you need to be aware of in terms of the ions. You got to add up all the ions to get the correct concentration to know if it's an isotonic solution or not? All right. So dealing with these things then, one of the questions from the book, why can't you drink seawater even if you're stranded on an island getting thirsty? Okay, so what does that do? How does it shrink your cells? Yeah, so that salt water is going to be a hypertonic solution, right? Which means it's going to draw water out of your cells, cause you to collapse.
Can't you like boil the water
Sure,
and then
and get the salt out of it.
Yeah.
You can't just boil it. You have to actually distill it. You have to evaporate all the water, collect it somewhere else. If you just boil salt water, it's still salt water. There's still salt in it. But what you can do is you can evaporate all the water, catch it on like a trap of some sort, and then have it run somewhere else.
What do you mean? No, like boil this like.
Okay, so like one way you could do it,
Water.
you could take a bunch of seawater and put it in some kind of a container, and then put an empty container in the middle, and put some kind of a plastic wrap or a leaf or something on the top that's slanted in toward the middle. So that as the water heats up from the sun on the outside, salt water, it evaporates, then condenses on the leaf and runs down into the cup in the middle. And then the stuff in the cup in the middle would be pure water, because all the salt would be left behind, would not evaporate. It's a lot of work, yeah.
I know some drinking is just like that kind of process.
Mm-hmm.
We do that.
Yeah.
When you collect just a bad one.
Mm-hmm. Right, yeah. Yeah, so when you do it with something like wine, you can just take the alcohol out. But you have to be careful because you can also concentrate dangerous byproducts like methanol that way. So you have to like throw out the first little bit, because that's where the more dangerous stuff will concentrate. Okay. All right, so that's solutions. So the major things for the solutions that you need to be able to do are be comfortable with molarity, calculating molarity, and dealing with moles per liter, that kind of thing, because it's an important designation. And then some of the terminology. And as usual, look at Blackboard for the specifics of what you're going to need to know for each of these. We'll have a quiz on the solution stuff next Wednesday.
Oh, that's nice. Next Wednesday?
Quiz next Wednesday on solutions. All right. And how they relate to other things. So let's look at how some of these concentrations can be used in the context of a chemical reaction. 7. So we just finished 7. I think, as long as it's still the same. We just finished 7. I think 7 was solutions. 6 was gases. 7 was solutions. And we're just finishing that. All right, so we'll do a little calculation that will bring us in to the next topic here. Let's look at this reaction that we did in class, where we reacted zinc with hydrochloric acid, and that formed hydrogen gas and zinc chloride. So that's the balanced reaction. We dropped some zinc in hydrochloric acid, and it kind of bubbled. That was the hydrogen bubbles forming from this reaction. So normally we would look at a reaction like this from the previous stuff that was on the exam, and I might say something like, well, how many grams of HCl do you need to react with 20 grams of zinc or something? So let's say we know that we have 20 grams of zinc, and we want to know how much HCl we need to react with it. So we go through and do the mole calculations and all that business. But that's not really going to help us here, because HCl is not usually measured in grams. HCl is a gas by itself. It's a really dangerous gas. We don't really keep it around. So if we're reacting something with HCl, what are we probably using instead? Instead of hydrogen chloride gas, what are we? Well, yeah, but let's say we don't want to deal with the gas at all. How do we usually see HCl in the lab? Yeah, it's in solution. So it's not actually liquid HCl, it's HCl dissolved in water. That's what we call hydrochloric acid. So hydrochloric acid is HCl gas that's been dissolved in water. So it's a solution. And we can't measure out grams of HCl in solution because it's all in with the water and everything. So if we want to know how much HCl to use, we have to take it from a particular solution. We have to use a concentration. So let's say that we go through our stuff and we find that we have 6 molar HCl. And we've used that. That's the relatively concentrated stuff that's in the dropper bottle usually. 6 molar HCl. So now we know something about what that 6 molar means. 6 molar means 6 moles of HCl in every 1 liter. So the question then is, how much HCl do we need? And this is going to be in milliliters to react with that 20 grams of zinc. We're going to use the concentration to figure this out. First, we need to know how many moles are in that 20 grams. So we've got to first convert that 20 grams of zinc into moles. We look up zinc, and it is 65.4. Divided by 65.4 is 0.3. Right? So that's saying that we're starting with 0.3 moles of zinc. How many moles of HCl do we need to react with 0.3 moles of zinc? Yeah, so double that, because it's 1 to 2. The ratio in the equation tells us that it's 1 to 2. So that means that we know that we need 0.6 moles of this. We could set up that ratio, and we'd see that it's multiplying by 2. This is the same we did with the mass type equations, so this is not new yet. So the next part is the new stuff. We have to know how much. So our next question then, how many milliliters of 6 molar HCl contain those 0.6 moles? Sounds tricky, but really we just do it as another proportion, as another conversion. So we say 0.6 moles of HCl. And instead of moles, we want liters. So we want to do a conversion that cancels moles and gives us liters, which is just the concentration. So the concentration tells us that there are 6 moles for every 1 liter. So 0.6 divided by 6 is 0.1 liter. 0.10. I guess we'll keep that in there. So we need 0.10 liter of 6 molar HCl, or we could also say that's 100 milliliters. And 100 milliliters of HCl we can deal with, right? We pour it in our graduated cylinder and dump it in the reaction. So by knowing the concentration, we can find out exactly how much of the solution to use in our reaction by keeping the molar amounts equivalent. Okay, let's try something similar. Let's look at just that last question, because that's kind of the newest part. And I'll give you a question that's just like that. So how many milliliters of, let's say this time, is 0.100 molar sodium chloride solution contain 0.03 moles of NaCl? So how'd you set that up? Yes. Yeah.
We got 0.03
Mm-hmm.
moles.
Right. Okay. Yeah, so we're going to use the concentration here. This is going to be moles per liter. Right? So that's going to be 0.3 liters of the solution contains 0.03 moles. But the question asks for milliliters, so that's going to be 300 milliliters. All right, good job. So really, that's the only new part of the previous question. The previous question seemed really long and involved. But all this part, getting to this 0.6 moles, was all the old stuff. Converting grams to moles and then using the ratio from the equation to figure out how many moles from another one. The next part was the new part, how to use a solution to figure out how much you need. So you can see how this might be a lot more difficult if that solution were reported in percent instead of molar. If that were in percent mass per volume, you'd have another conversion to do, because you'd have to turn the solution from grams to moles first.
So you wouldn't give us.
But I wouldn't give you that, because. But seriously, I mean, you wouldn't use that. So if you're doing a chemical reaction, you're not going to use a solution that's in percent concentration to calculate exactly how much you need for a chemical reaction. So you'll notice in the lab, or maybe you have noticed, sometimes we use solutions that are reported in molar. Sometimes we use solutions that are reported in percent. If they're reported in percent, it's usually because we don't actually care how much is there. We just need some of this stuff. So it's like a 1% solution or something. Just means we need some. If it's reported in molar, chances are we need a specific amount, like 1.0 milliliters or 2 drops or something like that, because we're using it to match up mole to mole with a very specific reaction. So that's why you see both types of designations. The percent composition is a lot easier to make. The molar is a lot more useful in a reaction. Okay. Yeah, so you'll notice technically all that stuff is in there, but the major focuses of the goals or the objectives for that chapter are to be able to deal with molarity populations, because that's what's most useful to us in reactions. Okay, so let's move on. A little behind. Actually, I'm going to start a new. We're working on this one for a while. Now let's look at acids and bases. Anybody heard these words before?
Yes.
Yeah?
pH in your
Okay.
blood.
What?
pH in your blood. Cool.
pH?
Yeah, pH is 7, cool.
Okay, so you gotta take pH. What's the pH a measurement of?
Yeah,
Hydrogen ions. Okay, how does that relate to acids and bases?
acid has more hydrogen than the base.
Yep. So is that a higher pH or a lower pH?
Acid has a lower pH.
Acid has a lower pH. Yeah. So we'll get into all this stuff. What are some examples of common acids that you might encounter?
Acids.
Orange juice. Yeah.
Vomit.
Vomit. Hopefully not at the same time.
Your pee, isn't that acidic?
I believe so.
Vinegar.
Vinegar. Soda. Soda is really acidic. You can clean metal with soda.
Really?
Yeah, you can like polish car wheels with
Good stuff.
Is it true that?
phosphoric acid.
My aunt was doing her laundry one time, and this might just be like really weird. I don't know, it was really weird, but she put like soap, like Coke in the clothes. If you're not in your head, like that's right. Okay, so my family sound crazy. So like, yeah.
Maybe.
She like puts like not like a whole can, you know, it's
Right.
just a little bit and like
Yeah.
apparently it cleans.
I can see that because sometimes you put vinegar in there. I think it's less of a cleaner for clothes, but than a fabric softener, because the acid breaks down some of those minerals that lead to the kind of hard, scratchy clothes, and so makes it a little bit softer. So maybe I would be worried about like staining and stuff a little bit though. Yeah, maybe not with the whites. I don't know. So anyway, so everybody experiences some acids. What about bases? What bases do you use? Ammonia is a base.
What's ammonia?
Ammonia?
Yeah.
Ammonia is the way we experience it is a cleaning solution. Smells really strongly. It smells like
Isn't
cat
milk
meat.
an acid?
Right, so antacids like milk of magnesia, those are bases usually, or actually related to bases. Milk itself is pretty neutral. It's what's called a buffer, which means it doesn't change its pH very easily. Eggs? Good question, I don't know. Basic flavors, basic foods tend to taste a little bit bitter. And so there's very few basic foods that we use. Baking soda would be an example, but cranberry and cranberry juice is an example of something that's a little bit basic. But there's very few examples of that. We're usually not as experienced dealing with bases. And then really strong cleaners are usually basic. So things like ammonia, have you heard of lye?
Yeah.
Or lye or caustic soda is sodium hydroxide, and that is used for really severe cleaning metal and things like that. Can clean bones, that kind of thing with it. So the first thing I guess I want to talk about with acids and bases is just to get rid of that idea that acids are more dangerous than bases, because that's really not true. They can both have examples of really dangerous things and things that are not so dangerous. And it's not that one is more dangerous than the other. So something like lye is extremely caustic, extremely bad for your skin, just like a strong acid is. And then, of course, there's acids like orange juice or vomit that aren't going to hurt you that much. Or vomit orange juice cocktail.
Okay.
I'll save these notes here.
Isn't like sour stuff, like sour candy also?
Yes, sour candy is extremely acidic. That's why it's bad for your teeth. All right. So let's look first about naming acids, because we all like naming things, right? Acids are usually named from the ions. So that's helpful because we know all our names of ions. If it's just one thing, just one ion, you put a hydrogen on it and you've got the acids. So chloride, for instance, gets a hydrogen and becomes HCl. So the new parts are hydro and then ic acid. So you've got hydrochloric acid, hydrobromic acid, hydroiodic acid, hydrofluoric acid. All of these are named in this way. Hydrocyanic acid from cyanide. Other ions don't put the hydro in front. So if you have, let's say, NO3 minus, which is called what? Right, nitrate. And that gets its hydrogen, becomes HNO3, which is nitric acid. So you can have nitric acid, phosphoric acid, sulfuric acid from sulfate. So depending on what which ions they come from, that's where the name comes from. And the most common ones are hydrochloric, nitric, phosphoric, sulfuric, and then carbonic acid, the acid of carbonate. Now you'll notice some ions, like let's say carbonate, what's the charge on a carbonate ion? Yeah, that one's 2 minus. So when that becomes an acid, it's actually going to get 2 hydrogens and become H2CO3. And that's carbonic acid.
So it gets 2 because of charge of 2.
Right. It needs 2 of those hydrogen ions to balance out its 2 minus charge. Right. And there's no special names for bases. They're just named, they're usually ionic compounds and they're just named like ionic compounds. So sodium hydroxide is a base, calcium hydroxide, ammonia is its own kind of name, but nothing is like something base or base something or other. That's not named that way. All right, so that's the basic naming. So then we really should define here what exactly makes an acid or a base. And there's actually a few different definitions out there that are used in different situations. We're going to focus on the most common most useful one for our purposes. And you don't need to really know this word, but this is called the Bronsted-Lowry definition. And it looks like this. Acids are molecules or atoms that donate hydrogen ions. So they are hydrogen ion donors. That's what we say an acid is. It's a molecule that gives up a hydrogen. And so then what do you think bases are? Yeah. Bases are molecules that accept that hydrogen. So acids give the hydrogen, bases accept it. Now the key to this definition is this defines the roles that these things take in a reaction. So it does not say that you can just look at any molecule and say, oh, that's an acid or that's a base. Not at all. You have to look at a reaction and actually see what's happening. Is the hydrogen going from here to here or from here to here? Depending on where it's going, that's how we assign acids and bases. So let me give you an example. So this is ammonia, NH3, in water. You put ammonia in water. It actually can go either way, so we'll put 2 arrows. It forms ammonium ion and hydroxide ion. So look at this reaction going from left to right, the forwards direction, from left to right. Where is the hydrogen coming from and where is it going? So which molecule here is donating the hydrogen and which molecule is accepting the hydrogen? Yeah, H2O is donating the hydrogen because this is H2O here, and then over here it's just one H. So it lost a hydrogen. That means that in this reaction, this is acting as the acid. It's giving away its hydrogen. And then that means that this one is the base because it's taking the hydrogen. So it goes from NH3 to NH4 and gets a positive charge because now it's ammonia. So that's what we mean by a role. We wouldn't say that water is an acid as just like a general property of water, but in this reaction, it is acting like the acid. It is the acid in this reaction. So when we look at an acid-base reaction like this, we can also look at the backwards direction and find acids and bases. So imagine now that we're starting here and going to the left, which thing is losing its hydrogen going from right to left? Yeah, the NH4 is losing its hydrogen because it's going from 4 to 3 as we go right to left. So in the backwards reaction, this one is the acid. And then this one is the base because it's going from OH to OH2 or H2O. And this will always be the case for acid-base reactions. They're reversible, and each base will have what we call a conjugate acid and vice versa. So these two species here are known as conjugates. So we would say that NH4 plus is the conjugate acid of NH3, or NH3 is the conjugate base of NH4 plus. Right, it means that one is the other one missing or gaining a hydrogen. And then the same thing here. So the conjugate base of H2O or of water is hydroxide. And the conjugate acid of hydroxide is water. Let's look at another way that we can have a reaction with water. Let's take HCl, hydrochloric acid, and react that with water. The products from that reaction are chloride and this kind of unusual molecule, H3O+. H3O with a positive charge. That's an ion. It's an important ion. This is known as hydronium ion, like water with an extra hydrogen and a positive charge. So going from left to right, which is the acid and which is the base on the left side? Which is acting as an acid, which is acting as a base on the left side? Yeah, on the left, the water is the base. So the HCl is giving up its H and becoming Cl minus, going left to right. The H2O is gaining that H and becoming H3O plus. So we have hydrochloric acid, our acid, water, our base. So then what about on the other side? It's the opposite. So the conjugate base of HCl is chloride. And the conjugate acid of water is this hydronium ion. Now the reason that hydronium ion is important is because that's what actually exists when an acid dissolves in water. Remember we talked about how hydrochloric acid is really a solution in water of this hydrogen chloride gas. So if you take HCl gas and you dissolve it in liquid water, this thing that you form, this mixture of chloride and hydronium, that's actually what we call hydrochloric acid. So whenever you dissolve an acid in water, you're actually making hydronium ions. That hydrogen is sticking onto a water molecule and making a hydronium ion. I'm putting a third hydrogen on there. And so that's really what's existing inside that water solution. It's not really free H ions, H plus ions floating around. It's H3O plus hydronium ions. So one thing that I want you to be able to do is to come up with conjugate acids and bases given just a formula. And we do that by going back to this definition. Acids are molecules that donate H+. So if we want a conjugate base of a particular acid, we take away H+. Let's look at how that works. So I might say, what is the conjugate base of water? And to figure this out, we'd take water, H2O, and we'd get rid of an H and a plus. So if we get rid of an H, what's left? There's an O left, and there's another H left, right? And then we get rid of a plus, so what happens? What does it mean to get rid of an H plus? Yeah, it means that we have to deal with the charge as well, because the hydrogen that's leaving is not taking its electron with it. It's leaving its electrons there. So if our water has a neutral, no charge at all, and it loses a positive something, that means that it's going to end up being negatively charged. You see that? So this is hydroxide ion. Sometimes we write it OH, it doesn't matter. And this is the biggest mistake that I see people make in doing this kind of work, is everybody understands, okay, we take away the H, that's easy. But we also have to remember to change the charge because a positive thing is leaving. Right? So if I ask you what the conjugate base is of H2O, you want this thing to lose H plus, meaning lose an H and lose a positive charge. If you lose a positive charge from a neutral compound, you're going to end up with a negative charge. If that hydrogen leaves its electrons behind, that resulting species is negatively charged. Okay. Let's try another one. I'll just say CB, same thing, of ammonium, NH4 plus. So if we lose H plus from NH4 plus, what are we left with? If we lose H plus from NH4 plus, what are we left with? NH3. Well, careful here. This started out as plus, right? So if we lose H plus, then we're just ending up at neutral. Another way to think of this is that whatever you make as the conjugate base, if you add H plus, you should get to whatever you started with. Right? So if you have this neutral NH3, you add a hydrogen and a positive charge, you've got NH4 with the positive charge. Up here, if we took hydroxide and we added H plus, we'd have a negative and a positive. They'd cancel out and we'd end up with neutral water. All right, so we got to make sure to change our charges accordingly. Let's try going the other direction. What is the conjugate acid of let's say cyanide? Cyanide is Cn minus. So how do you find a conjugate acid? That means that what? Well, what does an acid do? The acid donates. So if we want the conjugate acid, that means that this thing is going to be acting as a base. Cn minus acts as a base, grabs an H plus, and then becomes an acid, becomes its conjugate acid. So what we want to do then is look at Cn minus plus H plus, and what do we get? HCN or CNH with no charge anymore because the negative and the positive cancel out. So if we're looking for a conjugate acid, we're adding that H plus because this thing is acting as a base. If we're looking for a conjugate base, we're giving that up. Good so far? Okay. That's a good stopping place. So next time we'll talk about strong and weak acids and bases and pH. And we'll have a quiz on the solution stuff. Yeah. Right.
You said there's more